In 2006, a team of researchers collected DNA from every wildcat species on the planet, all 37 of them. From the Siberian tiger to the black-footed cat in the Kalahari, from the snow leopard on Himalayan ridges to the flat-headed cat wading in rivers of Borneo, every cat species still alive. Then they sat down and compared all of it. The paper came out in Science that year. The lead author was a geneticist named Warren Johnson. And when other researchers read what the data showed, the first reaction in a lot of cases was disbelief, because the family tree that came out of the DNA looked nothing like what anyone had assumed. Before that study, the way scientists grouped cats was mostly based on how they looked. Big cats together, medium cats together, small cats together. The lion, the tiger, the leopard, the jaguar, all enormous, all roaring, clearly in one group. The cheetah had spots like a leopard and lived in Africa like a lion, so it sat near the big cats. The clouded leopard had spots too, and was a decent size, so it ended up somewhere between the small cats and the big cats in most classifications. That physical approach had worked well enough for a century. Then, the DNA came in and took it apart. The researchers weren't just mapping family trees out of academic curiosity. They wanted to understand something specific. How did 37 species of cats spread across nearly every continent on Earth actually relate to each other? Who came from what and when? To answer that, they used what's known as a molecular clock. The idea behind it is fairly simple. DNA mutates at a predictable rate over time, and by counting the differences between two species' genomes, you can estimate how long ago they shared a common ancestor. The clock isn't perfect, but it's far more reliable than looking at an animal's face and making a guess. What they found was that all 37 living cat species fall into one of 8 distinct lineages. 8 branches on the family tree, each tracing back to a separate common ancestor. And the branches don't fall where anyone expected them to. Take the cheetah. The cheetah is one of the most recognizable animals on Earth. It lives in Africa like lions and leopards. It has spots like leopards. It hunts by chasing prey across open grassland, the same terrain lions work on the Serengeti. For a long time, it was classified alongside the big cats, or at least near them. Some researchers thought it might be specifically related to the leopard given the similar coat. The DNA said no. The cheetah sits in the puma lineage. Its closest living relatives are the cougar, the mountain lion of North and South America, and the jaguarundi, a small otter-faced cat that lives in the scrublands of Central America. The cheetah is not a big cat. It never was. The spots, the African habitat, the open country hunting, none of that reflects shared ancestry with lions or leopards. It reflects a completely separate evolutionary path that happened to arrive at similar-looking results. There's a name for that in biology: convergent evolution. When two unrelated species independently develop the same feature because they're solving the same problem. The cheetah and the leopard both evolved spots, but they did it separately, millions of years apart on different branches of the tree. The cheetah and the lion both became African predators, but their lineages had already been separated for millions of years before either of them reached Africa. The cheetah's speed, which is unlike anything else in the entire cat family, evolved inside the puma lineage, not from big cat ancestors. Which raises an obvious question. Why did this one branch of the family produce the fastest land animal alive? The genetic data doesn't fully answer that, but it confirms that the cheetah's speed has nothing to do with the lion's strength or the leopard's agility. Those traits came from different trees entirely. Then there's the clouded leopard. Before the 2006 study, the clouded leopard occupied a strange middle ground in cat taxonomy. Too big for the small cats, too different from the true big cats. It had the largest canine teeth relative to skull size of any living cat, which put it closest to the ancient saber-toothed cats in that one physical trait. Most researchers placed it in a category of its own, somewhere between the big cat lineage and everyone else. The DNA confirmed that the clouded leopard is genuinely ancient. Its lineage separated from the rest of the cat family roughly 6 to 8 million years ago, making it the oldest surviving branch among all living cats. In genetic terms, a clouded leopard in Borneo is more distantly related to a tiger in Siberia than the tiger is to a house cat. The clouded leopard has been running its own evolutionary program for longer than almost any other cat on Earth. And then, in 2007, a year after the Johnson study came out, a second piece of news arrived. Researchers analyzing museum specimens and DNA from clouded leopards across Southeast Asia found that the animals on the islands of Borneo and Sumatra were genetically distinct enough from mainland clouded leopards to be an entirely separate species, the Sunda clouded leopard. A new cat species found hiding in plain sight on an island that people had been visiting for centuries, simply because no one had compared the DNA carefully enough until then. One genetic study revealed the cheetah was in the wrong group. A follow-up study found an entire species no one had formally recognized. The DNA was just getting started. Here's where the picture gets stranger still. The Johnson study mapped not just who was related to whom, but when and where each lineage first appeared. And what the molecular clock showed was that all 37 living cat species descended from a common ancestor that lived somewhere in Asia roughly 10 to 15 million years ago. Asia, not Africa. Africa is where most people instinctively picture cats, the Serengeti, the lions, the leopards, the cheetahs. But the origin of the entire cat family is in Asia. The common ancestor of every cat alive today, from the house cat to the tiger to the sand cat to the margay in the Amazon, lived somewhere in Central or East Asia long before or African savanna had the species it has now. From that Asian starting point, cats spread outward in waves. Different lineages moved in different directions at different times. The ancestor of the big cats, lions, tigers, leopards, jaguars, crossed into Africa and Europe around 6 to 7 million years ago. The ancestors of the ocelot group crossed from Asia into North America via the land bridge that once connected Siberia to Alaska, then moved south into Central and South America. The domestic cat lineage stayed closest to the original range, spreading across the Middle East and North Africa. The Americas had no cats at all until roughly 8 million years ago. The entire Western Hemisphere was cat-free. Then, the first wave crossed the land bridge from Asia, and from that single migration, every cat in the Americas descended. The jaguar, the ocelot, the margay, the puma, the jaguarundi, the bobcat, the Canadian lynx, all of them from one group of animals that crossed a land connection that no longer exists. Some of the most striking findings from the genetic work weren't about family trees at all. They were about what had happened to specific species over time. The cheetah's genetics are almost uniquely troubled. When researchers sequenced cheetah DNA and compared individuals from different populations, they found almost no variation between them. Cheetahs from East Africa and cheetahs from Southern Africa and the handful of cheetahs still living in Iran are genetically nearly identical. The variation you'd normally expect to find between individuals of the same species is almost entirely absent. The explanation is a population collapse. Somewhere around 10,000 to 12,000 years ago, at the end of the last ice age, cheetah numbers fell to an extremely small group of individuals. Every cheetah alive today descended from that tiny founder population. In the millennia since, the species has never recovered enough genetic diversity to replace what it lost. The practical consequences are real and strange. Cheetahs can accept skin grafts from completely unrelated individuals without rejection, something that would normally require a very close genetic match. Their immune systems respond identically to the same pathogens. A virus that kills one cheetah moves through a population with almost no resistance because there's essentially no genetic variation to slow it down. What caused the collapse? The DNA can tell us it happened and roughly when. It can't tell us exactly why. The most likely explanation is the mass extinction that ended the last ice age, the same event that wiped out the woolly mammoth, the giant ground sloth, and the cave lion. The cheetah survived that extinction, but only barely, and the genetic scar never healed. The puma tells a similar story with an unexpected twist. Pumas, also called mountain lions or cougars, once ranged across both North and South America. The genetic data from modern pumas shows the entire North American population went through its own collapse, also around 10,000 years ago. But the part is this: the pumas living in Yellowstone and the Rocky Mountains and the Florida Everglades today are not descended from the pumas that lived in North America before the Ice Age. The original North American puma went extinct, along with the mammoths and horses and American camels. The pumas living there now are the descendants of South American pumas that moved back north after the original population died out. Within a few thousand years, South American pumas reclaimed the entire continent. North America lost its pumas. Then, they came back from the south and almost no one knew it until the DNA arrived. The same broad picture holds for other species when you look closely enough. African lions, for example, show surprisingly low genetic diversity across their entire range. Genetic surveys of lion populations from West Africa to South Africa reveal that lions are far more similar to each other than the geographic distances involved would suggest. The data points to a relatively recent population bottleneck. Lions may have come close to extinction more than once in the past 100,000 years, leaving a founding group that spread back across the continent as conditions recovered. The lions that exist today are not an ancient stable population. They are the survivors of collapses that the fossil record doesn't fully show and only the DNA preserves. Now, for the cat that surprises people most when they hear where it sits on the family tree. Your house cat. Most people assume the domestic cat is a scaled-down version of the big cats related to the leopard or the lion, or at least some large African predator in a fairly close way. The DNA places the domestic cat in a lineage with animals most people have never heard of. The sand cat, which lives in the Sahara and the deserts of the Middle East and survives on sidewinder snakes in temperatures that would kill most mammals. The jungle cat, a medium-sized spotted cat across South Asia. The black-footed cat of southern Africa. One of the smallest wildcats in the world, at roughly 1.5 kg, and also one of the most effective hunters by success rate, catching prey on more than 60% of its attempts, a rate no big cat comes close to matching. The Chinese mountain cat, barely studied, barely photographed, living on the Tibetan plateau in near total obscurity. These are the closest wild relatives of the animal sleeping on your couch. Your domestic cat shares more recent common ancestry with a sand cat in the Sahara than it does with a leopard in South Africa. The leopard is not in the same lineage. The leopard's branch separated from the domestic cat's branch somewhere between 6 and 8 million years ago. To put that in perspective, modern humans and chimpanzees shared a common ancestor roughly 6 million years ago. The domestic cat and the leopard have been on separate branches for about as long. The big cat group itself had its own surprises waiting. Before the genetic studies, the assumed relationships among the big cats went roughly like this. Lion and tiger most closely related. Leopard somewhere in the middle. Jaguar and snow leopard as the outliers. The reasoning was partly geography, partly appearance. Lions and tigers are both large and lack spots as adults. Leopards and jaguars both have rosettes. The snow leopard was so different from the others that for decades it was placed in its own separate genus, distinct from the true big cats. The DNA reclassified the snow leopard. It belongs inside the big cat group after all. And its closest relative turns out to be the tiger, not the leopard, despite sharing that name. Two animals that look almost nothing alike. One built for high altitude and cold. One, the largest cat in the world, are closer genetic relatives than the snow leopard and the leopard. Two cats whose shared name implied a connection and whose DNA showed the name was just a coincidence. The jaguar's position shifted as well. Jaguars and lions are more closely related to each other than either is to the leopard, which is counterintuitive since lions and jaguars live on different continents and look quite different. But DNA doesn't care about continents or appearances, it records actual history. There's one more finding from the genetic work that tends to stick with people. When researchers mapped the geographic history of the cat family using the molecular clock data, they found that cats diversified remarkably fast. The entire spread of the family, all 37 species across nearly every continent, adapted to deserts and rainforests and Arctic tundra and mountain glaciers and coastal wetlands happened in a geologically brief window. From the common ancestor in Asia, roughly 10 to 15 million years ago, to the full range of species alive today, took only a few million years. That's quick by evolutionary standards. The radiation of the cat family happened alongside the global expansion of grasslands during a period of major climate change. As open grasslands replaced dense forests across Africa, Asia, and the Americas, new hunting territories opened up. Cats, with their basic hunting toolkit already in place, expanded into those territories faster than almost any other mammalian predator family managed. What this means is that the differences between cat species are in some ways relatively thin at the genetic level. A house cat and a tiger share the vast majority of their DNA. The basic template, retractable claws, forward-facing eyes for depth perception, specialized teeth, hunting instincts, is the same across all 37 species. What the clock shows is that in a few million years, that one template produced animals ranging in size from 1.5 kilo to over 300, living in every climate on Earth, independently developing spots and stripes and solid coats and tufted ears and flat heads and webbed toes, all from the same starting point. The cat is one of the most successful animal designs in the history of vertebrate life. The DNA study makes clear why. The basic plan is extremely good, and nature found 37 different ways to run with it. Warren Johnson's paper changed what biologists thought they knew about cats. Several findings had to be revised, several species reclassified, several assumed relationships quietly abandoned. The Sunda-clouded leopard was discovered partly as a consequence of the study creating a proper framework for comparison. Snow leopards got moved into the big cat group where they belonged. The cheetah was placed firmly in the puma lineage. But the finding that tends to linger, the one that took the longest to absorb, is about geography. Cats came from Asia. They spread outward in waves over millions of years, crossing land bridges that have since disappeared, reaching continents that were then colonized and abandoned and colonized again as climates shifted and sea levels changed. The Americas had no cats until 8 million years ago, then became home to more cat species than Africa. Africa, which most people picture as the center of cat diversity, was colonized by cats from Asia relatively late. And the entire family, every tiger in Siberia, every jaguar in the Amazon, every lion on the Serengeti, every sandcat in the Sahara, every cat watching you from across the kitchen right now, all of them trace back to a single ancestor in Asia, living in a world that looked almost nothing like the one those cats inhabit today. The results of the study shocked the researchers who spent their careers working with cats professionally. These were people who thought they knew the basic outline. Then, a single genetic comparison reordered the entire picture. What DNA keeps doing in study after study is show that appearance is a poor guide to ancestry. The cheetah looks like a big cat, and isn't. The snow leopard is called a leopard and isn't one. The jaguar and the lion are closer to each other than either is to the leopard. The clouded leopard turned out to be two separate animals. The house cat's closest wild relative lives in the Sahara. The family tree that emerges from the actual genetics is stranger and more interesting than the one scientists had before. And the cat on your windowsill carrying a genome that has been stable for thousands of years is a far stranger animal than it looks. It isn't a small version of a lion. It isn't a scaled-down leopard. It belongs to a completely separate branch of the family, alongside desert cats and jungle cats and a tiny spotted hunter on the African plains that catches prey more reliably than any big cat alive. The animal watching you across the room isn't a domesticated predator. It's the member of a lineage that made its own choices, spread across the world on its own schedule, and has been doing things its own way since long before anyone thought to compare the D and A.